This is lecture 5E for Calculus 1 on substitution. Here is the idea behind substitution. Say you have a function 3x squared times the cosine of x cubed, and you're looking for the primitive of this function. You can do it by pattern recognition. You can start thinking about it and say, well, the primitive of cosine is sine, and here's this x cubed, but I know that looks like a function that was a composition, so I would have to have taken the derivative of x cubed, and that would give me 3x squared, so I'm going to think that it is sine x cubed. Then I could verify what I did by taking the derivative. When I take the derivative of sine x cubed, I have to use the chain rule. To use the chain rule, I have to recognize that sine was the outside function and take its derivative, which gives me cosine of x cubed. Then I have to take the derivative of the inside function, which is the x cubed. I end up with 3x squared times the cosine of x cubed, which is what I wanted. So that verified my choice. That was very good, and it worked out that time, but the idea is we would like to have a more systematic way to undo the chain rule. The idea is that if you had a primitive, and by using the chain rule you created the derivative, if you're starting with that derivative, you use the substitution to get back to the primitive. So chain rule and substitution are in a way inverses. They're not exactly inverses, they are sort of inverse methods. And here's what we do. We're going to use certain notation here. We'll say that the derivative is f composed with u being the inside function, and we will change the variable from x, or t, to u. We will also change the limits of integration if it's a definite integral. Alright, so if I start here and I have limit of when I'm integrating with respect to x, and the lower limit is x1, right here, when I change to u, I have to change that lower limit of x1 to u1. I have to change the upper limit from x2 to u2. And then hopefully I'm left with an integral that's very easy to evaluate. I'm going to show several examples on how to use substitution. I think that might be the easiest way for you to understand it. So let's say I have a definite integral. I'm going to go from 4 to 10 of 2x times the cosine of x squared. So I change the interval by assigning u to be what I consider to be the inside function. Looks like x squared is the inside function. Then I have to change the, I'm going to change variables, so I need du. I'll take du by dx, and that will be 2x. So du equals 2x dx. I just multiply both sides by dx to get that. Although at this point you would say that is not correct, because I've been saying all along d by dx is an operator. But there you go, do it anyway in this case. Alright. I'm going to show several examples on how to use substitution. I think that would be the easiest way for you to get the idea of it. I'm going to start with the definite integral from 4 to 10 of 2x times the cosine of x squared. I want to change the variable to u, and I will assign u to be what I think is the inside function. There could be more than one choice, but here let's just set u be x squared. Then I have to compute du by dx, which is 2x, and then I can say du equals 2x times dx. I need to change the limits of integration. At the lower limit, u would be 4 squared, which would be 16. At the upper limit, u2 would be 10 squared, which would be 100. With all these changes, the lower limit of 4 becomes 16. The upper limit of 10 becomes 100. I already computed all those out. The term 2x dx is replaced by du, and the cosine of x squared, well, x squared is u, so it becomes a cosine of u. I can integrate that easily and get sine u, evaluate it at 100, and subtract from that the value of sine at 16. Remember, even though the numbers don't look like they have pi's in them, They are still in radians, meaning that your calculator must be set to radians to work out the rest of this problem. That is how you do, that is how you would evaluate this definite integral. If the same 2x times the cosine of x squared was presented as an indefinite integral, then I'll show you what you have to do. Let me erase everything. Okay, there are no limits of integration to change. I do change the variable to du again. So the 2x dx becomes du. Since u is x squared, cosine x squared becomes the cosine of u. I find the primitive, which would be sine u plus c. At this point, you go back and find what u was and substitute it. There you go, sine of x squared plus c. Now here is this fundamental difference. If I'm doing the definite integral, once I change variable, I never go back to the original variables. I just keep working it out to get the number. If I have an indefinite integral, after I evaluate it and get the primitive, I'll have a u sitting there. Then I have to evaluate the u. I have to substitute what u was. In this case, I had to put x squared back in. The reason you don't have to do that up here, you have a sine u as well, is because you already changed the 16 and the 100, and it's all taken care of. Second example, I'm going to integrate from 0 to 1 of this function. All right, so I want to change the variable. I'm going to pick what looks like an inside function. The inside function is probably 6x squared plus 6x plus 10. Your inside functions are often the argument of transcendental functions. Okay, du by dx is 12x plus 6, so du is 12x plus 6 times dx. I change the limits of integration. Okay, u1, I have to substitute the 0 in, and I find that the lower limit of integration is 10, the upper limit of integration is 20. With this changes, here's what I get. The 0 becomes 10. The 1 becomes 22. These terms, 12x plus 6 times dx, that all gets replaced by, ooh, that should be a u there. Let me change that. This is a u. Okay. Now, secant squared of this argument is really the secant squared of u. That is something I can evaluate easily. The primitive of secant squared is tangent. So I evaluate tangent at 22, the upper limit, and subtract from it tangent at 10. Again, remembering the calculator is in radians. Okay. What if this is an indefinite integral? We'll do the same procedure, but let me erase everything. This is for the indefinite integral. There are no limits of integration, so there's no limits of integration to change. I end up with the same thing, secant squared u du. Looks like I missed that again, 2 down there. Sorry about that. Change that to a u. There we go. Let me put that back to a u so that you always see that as u. All right, so now I have secant squared u du. I can evaluate that. The primitive is tangent u plus c. At this point, because I'm not putting numbers in, I would go back, find what u was, which is up here, substitute that, and that's my answer. So again, when you have the definite integral, once you change variables, and you've changed the limit of integration to those new numbers, you just proceed and get the answer, get the numerical answer. You're done. If it's an indefinite integral, once you're done, you'll have a u in the answer. Go back and substitute for that u, so you have everything in terms of x again. Here's another example. I want to integrate from 4 to 6, 3x times e raised to the x cubed. So I'm going to let my change of variable to u, I'm going to assign u to be what looks like an inside function, which is x cubed. Du by dx is 3x, so that means du is 3x dx. And the lower limit of integration is 12, becomes 12. Under u, the upper limit of integration is 18. Here are my changes. The 4 turns into a 12. The 6 turns into an 18. The 3x dx becomes a du. E to the x cubed is really e to the u. I'm done, and I can integrate that easily. That becomes e to the u, evaluated from 12 to 18, put in the numbers, and I'm done. Evaluate those numbers. If this would have been an indefinite integral, again, there would be no limits of integration to change. Okay, I would again end up with an integral of e to the u du. I know that the answer to that is e to the u plus c. But I don't leave it, the u, sitting there in the function. I go back and find out what u really was, which was x cubed, substitute that in, and that's my answer. Here's another example. I'm integrating from 1 to 6. 3 over x times the cosine of the log of x. I'm going to change variables. I'll let u be what looks like the inside function, which is a log of x. Compute du by dx and get 1 over x. So du equals 1 over x dx. The lower limit of integration u1 is 0 because the natural log of 1 is 0. The upper limit u2 is a natural log of 6, which is about 1.79. So here we go. The 1 turns into a 0. The 6 turns into 1.79. The x in the denominator here times the dx, that becomes the du. The 3 was just a constant. I can put that out in front. Cosine of natural log of x becomes the cosine of u, and now I can integrate this. It becomes 3 times the sine of u evaluated between 0 and 1.79. I put in the values, remembering 3 is outside of this. 3 multiplies the whole result. So 3 times the sine of 0 minus the sine of 1.79 is my answer. I'm done. If it's a definite integral, then I have no limits of integration to change. I will end up with exactly the same function, but with no limits of integration. I find the primitive. Remember, it'll have this constant of integration, but there'll be a u in it, right here. I change the u back to what it was originally, and that's the answer. I'm going to do one more example. Okay, let's go from 1 to 6 of x squared, 10 raised to the 12x cubed. Okay, it looks like 12x cubed is an inside function, so I'll change the variable that way. U equals 12x cubed. Du by dx is 36x squared. Alright, so du is 36x squared dx. I'm missing the 36, but I can multiply and divide by 36 and capture that. But the limits of integration, the u1 would become 12 at the upper limit. It would be 1292. So here's my problem. The 1 goes over here and turns into a 12. The 6 turns into 1292. I'm going to multiply and divide by 36, so I get my missing 36. So here's what I get here. Go to the green. I will take this 36 and the x squared and the dx. I can replace all those by du. Okay, I'm okay there. I still have a 1 over 36, but that's just a constant. It comes out in front. The 10 raised to the 12x cubed is 10 to the u. So I have the integral 1 over 36 in front, going from 12 to 1292 of e to the u du. I can evaluate that. The primitive of 10 to the u is 10 to the u divided by the natural log of 10. I assemble all that and evaluate between 1292 and 12. If this was an indefinite integral, I would have no limits to change. That 1 shouldn't be there. Let's see, forget that guy. I'll cross it off. Okay, forget about that. That isn't even there. So I have the same problem. I end up, after I make the change of variable, with 1 over 36 multiplying 10 to the u du. I take the primitive of 10 to the u, which is 10 to the u, divided by the natural log of 10. There's my answer, but I have a u in it. So I go back to my original value of u in terms of x and substitute it, and that's my answer. I think the best thing to do to learn this is to look at these examples I did as like little, I don't know, templates to follow, little examples to follow. Try to do some on your own. In most of the homework cases, I have given you what you a suggestion for you. Then after a while, I don't give you a u. I think you can figure it out trying to look at what looks to be the inside function and just follow this procedure.